Okay, well, thanks everybody, and I'm sorry that I can't be there today to give this presentation to you all. We're going to be talking about the role of machine learning with core scanning data, and we're going to use a couple of case studies from an iron ore and a porphyry copper deposit that my colleague Reza and I have been working on over the last few months. So this presentation is going to go over a little bit of the summary of that, and then also deal with some of these case studies specifically. So I want to start this presentation by outlining the challenge of subjective data, and this is really where I want to start, because part of what we have with a lot of our objectives is people dealing with description of core. So for example, let's take this core on the screen that you can see here. How can we describe this core? What's the best description that we could give it? Now, is it brownish gray? We describe it by color. We can talk red and gray bands. We can talk about lithology, banded hematite. We might talk more descriptive, a laminated iron silicate, or indeed talk a little bit about what it is. It's a banded iron formation. This comes back to what the Simon was talking about in the first talk, that often geologists are interpretive or descriptive, and it can lead to a lot of difficulties when we think about the data set that's given for analysis. Quite often, subjective data like description is poorly consistent. It can vary between different geologists. It can vary with time and history. It can result in a lot of sampling bias. Some geologists like to sample certain things. They sample the things that are interesting, or the things that are not interesting, or a bit in between. And it can also result in depth discrepancy. So what depth and where we put that tape measure and what we record on our sheet. We also need to deal with subjective data in a historical sense. Terminology in geology changes with time. What we call one thing one time and what geologists like to describe, and then we change the rules and call things differently. So this data set often doesn't lend itself quite well to dealing with the more common data science techniques. And of course, it leads us to two questions. Can we trust this data? And are these data representative of the rocks that we want to try and mine and we want to try and extract? And so this is often the challenge with subjective data, and where core scanning instruments come in. So a lot of the case studies that we're going to be showing you today are going to be based on using the box scan, which is a multi-sensor core scanner using the Olympus Banter, the TerraSpec VNIR Sweer, PointMag SAS, line scan cameras, etc. And importantly, not just the box scan, but other core scanners out there as well. They provide a consistent and objective or unsubjective and depth co-registered data set for characterizing the core. And in the case of this box scan system, it's multi-sensor as well. So lots of different sensors, all in a consistent way. And this really is the foundation that we build on for data science activities. And we do need the form of data science to understand these data sets, because core scanners produce enormous quantities of data. So to give you an example, in one day, we can produce thousands to tens of thousands of individual points. We can produce tens of thousands to hundreds of thousands of pixels of information across 20 or plus minerals. And when we talk about the new technology that some of the work that Geotek's working on here, like LIBS, there's over 100 times more data per meter. This really is big data, and the study of big data is data science. And core scanning data is the fuel for this new approach to geoscience, because it's consistent, it's objective, and it allows us to use these data science techniques to really unlock the secrets of this subsurface. And we're going to show you in this study two examples of cases where we've used data science techniques, one in an unsupervised exercise for iron ore, and one for a more supervised exercise in sulfide segmentation using images. So to get stuck into it, the first one is an unsupervised clustering technique for iron ore, and I thanks to Vale for allowing us to publish. This was originally presented at CIMEMEX-MIM last year with our colleagues in Geotek Brazil. And the data was acquired from the LEAP lab at CTF in Vale, where we've got 3 core scanning pieces of equipment all installed in the lab. And we're doing physical properties, hyperspectral imaging, chemistry, mineralogy, and photography all in one lab. And the geology, the challenge and the geology here is we want to try and have a data-driven approach to lithology throughout the entire of the quadrilateral peripheral region in Minas Gerais. This is a massive area of Minas Gerais, and we're trying to create a data-driven approach for lithology. And that lithology is pretty varied. Most of this study is going to deal with ytterbites and phyllites and other iron ore lithologies like hematite and quartzite, which Vale use here. But the objective and the problem here is that there's no consistent way that this lithology terminology is being applied over 50 years plus worth of mining. So can we use LEAP core scanning data to predict lithology without the need of a very complex training data set, which also doesn't really exist because of that consistency? Now, to do this, we used a multivariate approach, and we're trying to use, and we've used principal component and k-means clustering to predict lithology, to try and improve standardization across the geology teams and discover what we might not know about this lithology as well. So where do we start? We start by looking at some core logs, and we want to try and understand what are the important data attributes that we see. So on the left-hand side of this plot is lithology. This is from the Vale geologists' observations. We've got RQD, dry image, some petrophysical properties, some hyperspectral and mineralogy data and chemistry, all on one plot presented as waterfall plots. First thing, we're going to have a look at this sort of bottom section here where we get a bit more variation. The first thing we see is this really nice band of hematite. This is the red lithology colors here. And the hematite, we can see characteristic, lots and lots of iron, lots of very little silica and aluminium, and composed primarily of our iron oxide minerals. But there are variations within this hematite, and some of the biogeologists have got these two talc schist beds here that are present in between. But the chemistry tells us there's a little bit more going on, and the mineralogy tells us that there's quite some variation in the iron oxide minerals, and that translates into the petrophysical properties as well of this rock with the P&S wave and the density. So there's a little bit more happening here, and perhaps this can be separated into the different units. Same is true down in the quartzite. This is actually what they call ferrous quartzite. Down at the bottom, you can see the iron content, and again, perhaps there are more units to be seen here, and there are features that tell us something about it. So this tells us that the core scanning data is giving us information about stratigraphy, and it gives us a guide to what features or data might be useful for predicting lithology. But we have to select which are the most important features. And we've done this based on 5 key things. We've got application, geology, quality of the core, objective, and the reasoning behind it. These are 5 important bits. The application, what we're trying to do is predict lithology. And in some cases, we've got to do that from chemical ratios. So understand how do Vale geologists do this originally? And that's often from iron and silica and other deleterious metals that come about. We've got to keep in mind that the features we select have to be able to separate quite a varied geology: carbonates, phyllites, banded iron formations, quartzites, intrusive and extrusive volcanics, just to name a few. We have to bear in mind core quality. Most lithologies here are friable, and RQD can be very low, so we can't necessarily choose parameters that are affected very deleteriously from these very broken up materials. We have to make sure that we have parameters that can be acquired on a variety of different core qualities, because of course, some of these rocks are very economically important, so we must keep this in mind. We have the objective and to produce lithology, keep that in mind, that's our goal. We can also go down other tangents, but we've got to keep that as our mind, as that's our goal. And of course, the reasoning, we've got to review our logs and keep that geological understanding to come back through. So we've got to keep our feature selection reasoned with what we're trying to achieve, what we do. The methodology then takes, we've reasoned out using our principles, 44 different minerals or different features that we'd use. They're separated by chemistry, mineralogy, and physical properties, ensuring that we get a good range of information that comes across from these different lithologies. We go through a principal component analysis to dimensionally reduce this data, and we use a series of statistical methods to choose what is the right number of components of the data sets that we do. In this case, we've used 3 different components, and we go through a clustering exercise. This clustering exercise groups the data, so where they have similar chemistry, mineralogy, and properties, into a series of groups or clusters that separate out. And the next stage is then to go back through this reasoning section as well, because this is so far is just mathematics. Now we need to go through and look at the statistical functions. What is the right number of clusters? And we can use some statistical measures to do that, but also geological sense. So what is the right number of clusters from a geological sense? How many lithologies do I have? What are the different types of rock types that we have? But of course, to remember that data in each cluster has a similar chemistry, mineralogy, and lithology across this, which means, of course, that's exactly the same as lithology. Lithology has a similar chemistry, mineralogy, and physical properties as well. So that means that we can, with reasonable confidence, say that our clusters are related to lithology, and we term these to be lithofasces. And each one of these lithofasces we can give a description. In this case, we have 8. So the statistical measures and the geological reasoning tell us that we have 8 clusters or lithofasces, and we can analyze those now by using a series of ternary diagrams and other statistical measures to see how that relates to lithology. This is just one such of those diagrams: iron oxide, silica oxide, and aluminium oxide at the top. And the colors that you see are the different clusters represented on the lithofasces on the right-hand side. And you can see that we get good separation of our clusters in this chemical diagram. Now, to lithology, they separate really nicely. We have our hematites down here, high iron and silica. We have our ytterbites in the middle with a mixture of both, different types of ytterbites and silica. Phyllites and schists over here, and our ferrosilicates. The thing to notice here is that we do see iron-rich lithologies separated nicely, but also you get a lot of variation within these clusters. And that's where the subclustering, which I don't have time to go into today, comes into place, where we can look at the heterogeneity between each of our subclusters as well. So lithofasces do link to lithology. Let's go back to our log to summarize this case study. Now we have a case where we go back to our hematite section right here at the top. We come across on the right-hand side, and this is our lithofasces prediction. Again, we see a good response. We get lithofasces changes where we expect them in the geology. But critically, we see that this unit in the middle has much more chemistry and mineralogy similarity to the quartzites below. We wouldn't classify it as hematite. We also note that we see different types of hematite, one that is goethitic rich and one that is hematite rich, and that is separated out nicely from the statistical sense. And finally, down at the bottom, we have our quartzites, and our quartzites again we see as one continuous section mostly, but it's separated into 2 chunks, ones that are iron rich, more iron rich, and silica poor compared to the rest of the unit. So by using unsupervised clustering, we can create a data-driven approach to predict lithology. And not only that, we can see the heterogeneity within lithology. And we've applied this across the entire region of the QF region here using the LEAP core scanning data. So this is just one way of using machine learning or data science to predict this. The second way is using a more supervised approach. Again, we're using box scan. This is with thanks to Xanadu Mines, and this was presented by my colleague as Reza Ramdan up at IRIS in 2021. And we've taken about 30 kilometers worth of drill core images. And what we're trying to do here is to segment sulfide from the images themselves. And not only that, but go a little bit further and say, well, is it veined or disseminated sulfide? And can we produce images and make predictions based on what we have? Now, this is a much more complex problem, and we need to use a more supervised approach to doing it. So the first thing we do is have a think, well, how can we do this? So we turn to our trusty, faithful Google, and we can type in automated image segmentation Python, and we get a series of responses. We can do it by K-means clustering, XGBoost, random forest, UNet. There's a whole range of different things that we can achieve here. Now, all of them work reasonably well. You can use a variety of different ways of doing this, and it can segment sulfide pretty good until you get complications, problems. Sulfide minerals and these cores that we're looking at, this is a porphyry copper, I should have said previously, apologies. Sulfide minerals appear in multiple different forms. We have different forms like disseminated, veined, and massive. Their appearance is also different within the rock. So some of them are more dark, some of them are more shiny, some of them are difficult to see because, of course, they have a different background. And that means that the training data set that we feed into this model is much more complex And so we have to think about how we make our predictions. So we've created a much more complex way of looking at this problem. We take our data inputs from our training data, and the first part of our neural network that we're creating here is to predict lithology. So we've created an entire training data set just on the lithology part. And each lithology that we have has a separate neural network that will then go about segmenting the sulfide from the images. So the first step that we're trying to do is to say which lithology it is. And the second step is to try and segment our data set into the sulfide versus the background. And it's really important because one training data set doesn't apply to everything that we have. So we end up with a segmentation, and you can see an example of a segmentation here. The next stage we have to do is look at a workflow that enables us to say whether it's veined or disseminated sulfide. And this, of course, has big implications for the geometallurgy, but also the understanding of how sulfide is distributed throughout the size and throughout the core from geological history perspective. So we go through a series of different steps that we outline is here. We try to create polygons. We look at the shape of the polygons. We look at the roundness, and we try to see how close they are to one another so that we could go to the next step to say the red being veined and the yellow being disseminated. So we can start to create some statistics about where the sulfide looks. So how does that look for the larger picture? Here's a case. We've got 3 different examples from one of the boreholes here. This plot here is the extracted sulfide image. This is the original image. We've got our predicted lithology, which you can see on the right-hand side. We've got our predicted sulfide here based on what we see. And the cumulative plot is a proportion of veined versus sulfide. And what you can see is that the general trends, and this is sulfur assay apology in the black, and you can see that we get good general trends that match with this. And we can see that consistently. Here's a veined example. Here's a more of a massive sort of veined example disseminated. And here's a really good disseminated example through this brecciated horizon. This is really promising stuff. This shows our technique of extracting lithology and then through to sulfide has really opened up and given us some good opportunities. Let's go through this again, veined, more massive, and disseminated in really well. We can look at some statistics then about how that all matches together, and you can see some examples here. Now, while we get some pretty good trends, you can see there's quite a lot of variation, and that still exists because we should always bear in mind about what we're really looking at and what we're measuring. So the first thing is that some of these disseminated sulfides are very, very small. They're below the image resolution of what our camera is being able to get out in some cases. We should also bear in mind the difference between what we're measuring versus what is actually happening within the core from a sulfide perspective or an assay perspective. What we see on the image might be just a straight line, but it might be a completely angled vein going all the way through the core. And that changes the difference between an area measurement that we're making versus a volume measurement in the assay. And of course, we've got some other aspects as well of contamination of sulfur and other bits that the assay is picking up on. But nonetheless, even though we have these challenges still in our description of what we're doing, we're still able to get pretty good predictions of where sulfide is located. And not only that, but we get really good understanding of what is disseminated versus what is veined and how that links and changes throughout the different deposits. And we're now running this as standard across all the boreholes that have been collected throughout the deposit. So I want to summarize here in the last sort of minute or so of the presentation to really showcase what this is telling us. The first one is that data science techniques, and I do believe this wholeheartedly, unlock secrets of data sets in the subsurface. But to use these techniques, we really do need a consistent data set to start from, something that we can trust and we can see and is coming through with depth. And that's where core scanner data really do shine really brightly. They are the fuel. The data they provide is the fuel for this new approach to geoscience. There are 2 different techniques you could use, an unsupervised or supervised. Unsupervised is a really, and I hesitate to say this in some respects, simple to start and maintain with adding new data and understanding, but it can lack some complexity perhaps to solve some more difficult problems. And that's where supervised deep learning really comes into its own. It's much more challenging to undertake. You need a much larger learning data set. And of course, as you can see from our case study example, that learning data set can indeed need to be separated in a variety of different ways. but it does benefit from having a much more complex deliverable to solve a more challenging application, like in the case we've shown here with Xanadu. But we must always remember that core quality, rubble, solid, whole, pixel resolution, the dwell times of the sensors, the rock texture, even the geological geometry, veins, etc., all affect sensors differently. And from our belief and our part, multi-sensor scanners like we have with the box scan help to reduce this by spreading the understanding across multiple sensors, but they don't eliminate it. So that choice of data that we use, we must always bear in mind how we're collecting it and the physics of the thing that we're doing with it. But the opportunity is absolutely massive. Data science and core scanning really are hand in hand, and they're just the start of the discovery of what we're going to have to come. Thanks very much for listening, everyone, and I'm very sorry that I'm not there today, but I hope for any questions if necessary. Thank you.
Thank you, James. We've got a couple minutes for questions before we go for coffee, so if anyone's got any, then please stick your hand in the air. Right. No. Is this one working?
It's all right. I think I fixed it. I pressed the button. I was just wondering, with the iron ore dataset, the unguided dataset, did you build a 3D model from that? Because we've done lots of stuff with k-means, but actually realizing it in 3D is very difficult.
Do you mean a 3D model from a geological sense, or a 3D model from the PC, the principal component sense?
Just trying to build the predicted domains or the predicted lithologies in 3D. Have you tried to do that?
Yeah, we had a little look about using the 3D part and seeing if we can try and get any sense of our rationalization, but I don't think it was something that we really went down from that side of things. Not quite yet, no, is the answer. We had a little look about trying to visualize it. It didn't come out with anything major or spectacularly different, so we haven't gone down that road quite yet.
Thank you.
Okay. You hear me okay?
Hi there.
Okay. My question here is really just about the time investment to bring about that supervised kind of classification that you did. You know, how many hours, how many man and woman hours do you need to invest to create what you've done there?
Many, I think, is the answer. That's one of the reasons why I sort of say that the supervised learning data sets are much more complex and time intensive to get them set up and working. There's a lot of going around various different loops of understanding. I mean, I should say as well that what we've shown you there, we probably built that model 3, 4, 5 times in various different remits to see what would work and not work. So there's a good length of time that goes into investing in it. But of course, the output is a lot more complex than you'd otherwise get. So it's a well worthwhile investment, but it does take a significant investment to get going, and quite a lot of training data and marking up. So there's no way around that for sure. That's the advantage of the unsupervised approach in some respects. It's much easier to get going with it.
Hi. So how far do you think we're away from seeing this technology being commonly used on mine sites and projects?
Well, I think it's happening right now, actually, if I'm honest. I think there are plenty of companies out there that are actively doing this. And I think there are also companies that are investing pretty heavily based on using AI and machine learning with geological data to try and help predict the next drill hole or predict where their boreholes might terminate. So, and from a geological sense and exploration sense, I think that, you know, nearly every client that particularly that we have, the first question they're asking now is, right, let's do something with the data. And most of the cases we're going down now the routes of using, you know, data science techniques to help unravel what the data is telling us. Visualizing borehole logs gets us some of the way, and then to really extract the data is to use these new techniques and scientific techniques. So I think it's happening now, and it will only get it will only increase, and I think it will be rapid.
Thank you.